All right. Good morning, everybody. Let's go ahead and let's get started here. Let me start the clock. What I'd like to do today is I'd like to go ahead. I'm going to go ahead and finish up with the bonding. We'll try to get through that, and then we'll hopefully start our discussion bond energies and bond length. My hope is that we can get to that point today, but let's see how far we get with it. Okay. Because what I'd like to try to do is start Vesper. We'll start with um, yeah, Vesper theory. Hopefully, we can get that started on Tuesday, and try to get the lab going either Thursday or Friday. Okay, so that's the hope. Let's see how far we get today. Okay. The other announcement I want to make, and I'll remind you of this again in class tomorrow while we're taking roll, is that I've posted for you the chapter 8 homework for both the new edition for the new edition, and now I've also posted it for you. You can find that now on the post where I listed where I supplied you with the chapter 8 material. Okay, so the homework set for the new edition. Please go ahead and look there. If you're having some issues trying to find it, please let me know, and I'll help you find it. Okay. All right. So with that said, please make sure you come by, stick around after, or come by. I will be today, this afternoon. I will not be available for tutoring for office hours. I have a previous engagement. I have an appointment that I have to keep, but I will be available tomorrow after my 7th period class. But also tomorrow, if you have any questions about what we go over today, stick around after I take roll tomorrow, and then I'll answer your questions. Okay, or come by and see me on Wednesday. Okay, but yeah, let's go ahead then and let's get started. We left off with this idea of a double bond. What a double bond is. That's what we talked about on Friday. A double bond is the sharing of 4 electrons. So that is 2 pairs between 2 separate atoms. And the reason why the atoms would share 4 electrons instead of just 2 is because they both need the 4 electrons in order for them both to achieve their octet. So I hope then that you can see then that hydrogen is the one atom that will never form a double bond, nor will it form a triple bond. Okay, so hydrogen, whenever you see hydrogen in a molecular compound, it will always be a single bond. So as we go along and we're doing more and more of these structures and we're drawing them out, hopefully you're starting to pick up on some things that'll help you. Okay, so for example, hydrogen will always form a single bond. Hydrogen will never form a double or triple bond. Carbon will always be the central atom if it is present in a molecule. And so things like that, you got to be able to pick up on that as you go through these structures. Okay. All right, so let's go ahead then. On Friday, I left you with ethylene. So let me go ahead and let me open up my whiteboard here, and let's take a look at ethylene. Okay, let's draw ethylene here, and let's see how it looks. And let's see what type of bonds holds that molecule together. Now, as we go through this, remember, as I pointed out to you on Friday, make sure you keep track of the bonds. Obviously, you have to do that, but also keep track of lone pairs if there are any. The lone pairs will be very important as we get into the discussion of molecular geometry, which is the Vesper theory, which, like again, I said, hopefully we can get started with on tomorrow, if not, no later than Thursday. Okay. All right. So you got to keep track of those lone pairs. Okay. So let's go ahead then and let me open up and let me share this with you. Sorry. Okay. All right. All right, so let's go ahead and let's take a look at ethylene. Ethylene has the formula. So usually you will always be given the name, the name, or I will give you the structure of the compound, or both. Okay, so ethylene then, we left off with ethylene. As you notice, ethylene is not a binary, is absolutely not a binary molecular, it is a binary, sorry, molecular compound made up of 2 different elements here, but we don't, this is the, we don't name it systematically. So this is not dicarbon tetrahydride. Okay, we give it this name here. This is the name that it's given in organic chemistry. And for those of you folks who are going to be moving on, you'll be coming across that. Okay, but you could name this in the systematic way that we learned last week, so you can go ahead and name it. But the name that is most commonly used with this compound is ethylene. Okay? All right, so with the structure for ethylene, then what you want to do first is remember you want to draw out the, and initially go ahead and do this. You don't, hopefully later on you won't have to do this, okay? But as you start out and you're still working on this, I would suggest that you draw out all of the Lewis dot structures for all of the atoms involved. So you kind of have like, the idea is to have all the puzzle pieces in front of you. Now remember, carbon, when carbon is in the molecular state, it forms a set of what we call hybrid orbitals. And I mentioned on Friday that we will talk much more about that. Hopefully starting on Friday when we start talking about molecular theory. But if not, we'll extend it in the next Monday. Okay. All right, so with that said then, carbon, this is the Lewis dot structure for carbon when it is part of a molecule. Carbon, when it is not part of a molecule, remember, has one pair. There's 2 electrons that are paired up and 2 that are unpaired. In the molecular state, that is when carbon is attached to other atoms, it assumes this Lewis dot structure, it assumes that electron configuration instead. Okay? And again, we will talk about this much more on hopefully Friday, if not on Monday. Okay? All right, so how would we pair these up? Now, hopefully you see then that the carbons have to be kind of paired up with the hydrogen somehow, okay? And if you can imagine, if all 4 of these carbons surround all 4 of these hydrogens surround one carbon, and the last carbon, the one that's left out, won't be bonded to it. Okay? Because if you attach all 4 of these to one carbon, all the hydrogens achieve their duet, and the one carbon achieves its octet. All 5 of those are happy, but this one carbon is not a part of that bond. It's not happy. Okay? So hopefully you see then that based on what we've learned, okay, that the carbons, okay, will be kind of the center atoms. Now you can start playing around with this, and let's say then that if you had 3 of the hydrogens, let's go ahead and do this. Let's say 3 of the hydrogens attached to one carbon, and the 4th hydrogen attaches to the other carbon. Okay, we said then again, not all 4 of them can't be attached to one carbon. But what about 3? Let's see if this works. Okay, right. So in this case here, all the hydrogens have their duet. Okay, they seem to be fine. Okay, this carbon here on the left can only form one more bond, and it will be a single bond with the other carbon. If this is the case, this carbon now has its 8. Okay, so that's 2, 4, 6, 8. This carbon's happy. This carbon does not have its octet. It only has 1, 2, 3, 4, 5, 6. And so if we try to connect ethylene in this manner here, it will not work. Okay, so it won't work. So we got to go back to the drawing board. And this is how you want to go about working, doing these problems here, you guys. And that is, initially it's going to be trial and error, and it's going to be somewhat frustrating. But like I said, as you start doing more and more of these structures, you start picking up on little things. Okay? And I'll try to share those with you as we go along. Okay, that'll help you do these faster. Okay, all right. So if all 4 carbons can't be attached to one carbon, okay, I'm sorry, if all 4 hydrogens can't be attached to one carbon, and if 3 of them can't be attached to one carbon, let's try 2 on each carbon. Let's see how that works. Okay, so let's do this. And let's do this. Okay. All right. So with that said, we have a single bond forming here, a single bond forming here, a single bond forming here, and a single bond forming here. So again, same situation, but this time though, we've split the 4 hydrogens in half. 2 on one carbon, 2 on the other carbon. Okay. Right now, both carbons do not have their octet. If you notice that both carbons in house still only have 6. However, if you can imagine these 2 electrons pairing up, and then these 2 electrons pairing up as well, and forming a double bond, well, now let's count the electrons for each carbon. So this carbon on the left, we have 2, 4, 6, 8. You have 8 electrons for this carbon here. On the carbon on the right, same thing. You have 2, 4, 6, 8. And so this one double bond right here, and let's go ahead and label it. Okay, so you have one double bond. Okay, will allow then carbon to achieve then its octet. So in this particular molecule here, carbon forms a double bond with the other carbon, and it forms then 2 single bonds with the hydrogens. Okay, so in this particular molecule here, then we have 1, 2, 3, 4 single bonds, okay, and 1 double bond. Okay. And so that's the bonding that holds this molecule together. Okay, and if you notice, then we have no lone pairs. There are no electron pairs, so we have 0 lone pair electron. Okay. All right. So hopefully you were able to get this structure and write it down well. Okay. All right. What I'd like you to do then is let's go ahead then and let's take a look at what we've gotten so far. Okay. So this is ethylene right here. They had a double bond. I'll save this for you. Let's take a look at what we've gotten so far. Okay. So and I'm going to focus in on the diatomic elements first. Okay, so with hydrogen then, okay, what we saw with hydrogen then was that it was a single bond. And I want to emphasize here a new way that we can draw this. Okay? Okay. We can draw a single dash line to represent a single bond. Okay. Which means then if you, and this just saves us some time, because instead of having to draw the dots here and the bubble around it, that's what, if you can imagine, we can draw a straight line connecting the dots again. If you can connect the dots again right here, that's what this line here represents. And so I will start mixing in this way of drawing the structure. It's just a little bit easier, okay? But again, I will still be drawing the dots, Lewis dot structures, and we still need to connect the dots. But for the ones that we've done, already, I'm going to start drawing them this way so that you can see them. That's how most textbooks represent them as we move forward. Okay? All right, so we see then the diatomic hydrogen is held together by a single bond. Okay, no lone pairs on this one. So we have then single bond. Oops, let me go and do this here. We have 1 single bond. Okay, and 0 lone pairs. Okay. Now we saw another type of interaction, and we had the diatomic fluorine. Okay, so fluorine here is also a single bond, but we have then multiple lone pairs. And so if you take a look at this particular molecule right here, we have 1 single bond. And again, if you don't remember how that single bond is formed, please come by and we'll go. Okay, but this has 1 single bond, and here we have then 6 lone pairs involved in this molecule here. Okay, so 1, 2, 3, 4, 5, 6. Okay. All right, those are the single bonds, and then we looked at the diatomic oxygen. We saw that with diatomic oxygen we had then a double bond with 4 lone pairs. Okay. Right. And we saw that the reason why oxygen needs a double bond, one double bond, is that it needed those 4 electrons in order for both of these oxygens to obtain their octet. So we have 1 double bond, okay, with 4 lone pairs. Okay, all right. So with that said, then let's take a look at a third molecule here, and that is, let's take a look at N2. This is dinitrogen, or this is the elemental form of nitrogen. Okay? Let's imagine how nitrogen is going to form here. So let's go ahead and let's write out the Lewis dot structure for nitrogen. And again, let's put the pieces in place initially. Let's put the pieces in place at first. Okay? All right, so those are the 2 nitrogens right there. Okay? They both have 5 valence electrons. Okay? All right, so let's go ahead then and let's see how they will partner up. Okay, so I'm going to go ahead and I'm going to rearrange the Lewis dot structure just a little bit here, okay, to kind of help us with doing the connecting the dots here. All right, so let's imagine, let's say nitrogen behaves like hydrogen and fluorine, and we only have a single bond that forms between those 2 atoms. I hope you see at this point now, you guys, that a single bond alone will not allow either nitrogen to obtain its octet. Let's go ahead and count electrons. So we have 1, 2, 3, 4, 5, 6. Each nitrogen has only 6. So let's see if a double bond will work. Okay, so there it is. There's a double bond there. Let's go ahead and let's count electrons again and see if each atom has its 8. We have 1, 2, 3, 4, 5, 6, 7. Each nitrogen only has 7. So I think most of you by this point will see then that a third pairing has to occur there. Okay, and so with that third pairing, so we have 3 pairs now. With that third pairing, each nitrogen will have its octet. Okay? If you count it, each one will have this octet. So what we've drawn here then, what we've indicated here then, is that both nitrogens are held together by not a single bond, not a, and I'm sorry, I should write this in here, not a double bond, okay, that holds oxygen together, but we have then a triple bond. Okay. Right? And so if a single bond, you only have 1 pair of electrons that are being shared between the 2 atoms. In a double bond, if you have 2 pairs that are being shared by the 2 atoms, and I hope then you see then that a single line just represents a pair of electrons. Therefore, if you have 2 dashed lines, you have 2 pairs. So you have 2 pairs of electrons. And so in the triple bond, then we have 3 pairs of electrons that are being shared. Okay, so a total of 2 electrons here being shared, a total of 4 electrons here being shared, and a total of 6 electrons here that are being shared, and that is triple bond. And the reason why each nitrogen requires that triple bond to form is because that's the only way both nitrogens will be able to obtain their octet. Okay. All right, very good. Let's go ahead then, and let me save this really quickly. Clear this up. Let's take a look at an example here. Let's take a look at another compound, okay, molecular compound, and let's see what we have. So let's take a look at hydrogen cyanide. Okay, hydrogen cyanide. Okay, that's the name of the compound. Okay. And let's take a look at the formula for the compound right here. So it's going to be HCN. That is the formula for hydrogen cyanide. Okay. So let's go ahead and let's figure out what we have here. So let's draw the pieces first. Okay, so we have hydrogen, Lewis dot structure. Okay, with one electron. There's carbon. Okay, and there is nitrogen. Okay, there are the pieces of our puzzle. Now, the question then is this, and again, you know, like I said, as we go along, I'll point these I'll point out these little clues for you. But hopefully you recognize then carbon is right there. So carbon should be the center atom. Okay, so we're going to go ahead and we're going to draw the carbon assets. Okay, so there it is. There's our carbon. Now I hope then that you see then that the hydrogen now can only form a single bond. We already talked about that. So hydrogen can either form a single bond with nitrogen, or it can form a single bond with carbon. Okay, so let's go ahead then, and I'm going to go ahead and I'm going to draw nitrogen the way I did here. I'm just going to rearrange the dots again. Okay, all right. So if, let's say, hydrogen comes in and it forms a bond with nitrogen, there it is. Oh, sorry. There it is, the bond for nitrogen. And again, like I told you guys, this is going to be trial and error first. I mean, you're not going to be able to figure this out initially, but let's say it does that. Okay. Okay. Let's take a look at what's left. Now the carbon and the hydrogen the nitrogen have to bond together. So you can imagine then that electron gets shared right there, and that electron gets shared right there, so that we form then a double bond and a single bond here. Now, in this case then, the hydrogen is fine. It has its 2. The nitrogen is fine with that double bond because it has its 8. But if you notice, the carbon doesn't have, it only has 6. That's 2, 4, 6. So the fact that the nitrogen is attached to hydrogen won't work. It doesn't work. And so you have to go back to the drawing board and we got to try again. If that doesn't work, then we got to try something different. If the hydrogen isn't going to be attached to the nitrogen, then it needs to be attached to the carbon. And like I said, if you recognized early on, like I said, if you saw then that carbon is present, carbon's going to be the center atom, that means that hydrogen has to be attached to the carbon. Okay, so let's go ahead and let's do it right there. So there is the single bond between now hydrogen and carbon. What's left over? Well, let's go ahead and let's see. If these 2 electrons here are being shared, a single bond, neither carbon nor nitrogen will have their octet. If they share a second pair, again, neither one of them will have their octet. But if they share this third pair right here, now both the carbon and the nitrogen will have their 8, and hydrogen will have its 2. Okay. And so what do we have then? we have then a single triple bond. We have a triple bond here, and we have then a single bond. Okay. All right. So to summarize what we have here, then in this structure for hydrogen cyanide, then we have one single bond between carbon and hydrogen. We have one triple bond between carbon and nitrogen, and then we have one lone pair that sits only on oxygen. Okay, and so that's the molecule right here. Okay, all right. Let me go ahead and save this here, and let's practice this. Okay, and so if you need to, you know what, let me leave this up for you. Okay, and what I would like you to do is I would like you to draw the structure on your paper. Take about 2 minutes to do this for a molecule known as ethine. Okay. And it has the formula C2H2. Okay. So take about 2 minutes. Take about 2 minutes to draw the structure for ethine, and then let's compare answers once you are done. Okay. So take about 2 minutes, and then unpause the video, and then let's compare answers. Okay. So go ahead and let's see what you can come up with. Okay, let's see what you come up with. Okay, so again, I know that this is going to be tedious for me to keep doing this, but let's go ahead. I'm going to draw out the pieces. I'm going to draw out the pieces. That is, I'm going to write out these atoms here, the Lewis dot structures for these atoms here. So we have, there's one carbon. Okay, there's a second carbon. Okay, and then we have our two hydrogens right there. So we have all the pieces right there. Again, hopefully you recognize then that the carbons should be the center atoms. Okay. Now the question then is, will both hydrogens be attached to one carbon, or do we split the hydrogen? Okay. I hope then you see then that typically what we're going to see then is that the hydrogens will be split between, just like what we saw with ethylene. Okay, they're going to be split between the two carbons, and there it is. Okay, so we have them split. And then we will have then a triple bond between the carbons in order to complete the structure. So that we have then one triple bond and two single bonds for a molecule of ethine. Okay, so with that said, then we have then two single bonds, one triple bond, okay, and 0 lone pairs. Okay. And those are the characteristics of the ethine molecule. Okay, all right, very good. Let's go ahead then, and what I would like you to do is let's take a look at number 6 in your problem set. Take a look at number 6 in your problem set, and let's work through. We did the last one, so hydrogen cyanide's right there. So please make sure you draw that. And so I'd like you to work through the first two, so sulfur dioxide and the nitrate anion. Okay? And so we'll talk about polyatomic anions or polyatomic ions in just a moment, but I want you to give nitrate a try. Okay, let's see what you come up with, and take about 2 minutes to get that done, and then we'll go over together. Okay, so go ahead, take about well, hopefully if you need more time, take more time, then unpause the video. But take about 2-ish minutes to draw the structure for sulfur dioxide and nitrate. Okay, go ahead and let's get that done. All right, let's take a look at this here, folks. And let me go ahead and let me clear this out. Let's take a look first and foremost at sulfur dioxide. Okay, and here, if you notice, we don't have any carbons in it. So the question then is, which one's going to be the central atom? Okay. Again, as you do more of this, you're going to see then that carbon will be the center atom when you see it. Whenever you see carbon, carbon will be the center atom. Okay. Oxygen tends not to be the center atom when you see those. And so if it's a choice, if you have oxygen and some other atom element that it's attached to, it's going to be that other element that's going to be the center atom. And that's what we notice here with sulfur. Okay, so let's go ahead then. Let's draw the Lewis dot structures for each one of these again. Let's draw the puzzle pieces here. So sulfur then is going to be like oxygen. We have there. Okay, and we have oxygen. whoops, sorry. And the second oxygen. Okay. So those are our puzzle pieces there. Let's go ahead and let's take a look at how this is gonna, oh, you know what? I am sorry, you know, yikes. All right, that was my fault. That's my fault. I probably should not have asked you yet. We haven't quite talked about one unique type of bonding. So hold on to, let's hold on to this, okay? And we will work through this in just a moment. Well, yeah, just a moment. Let's hold off on sulfur dioxide. What I'd like you to do is, sorry, that was my fault. That was my fault. Let me go and clear this out. Let me ask you to do it instead, and then we'll come back to sulfur dioxide. So if you had some issues with that, I don't blame you. We haven't quite talked about a third type of bonding yet. All right, so let's talk about this third type of bonding right now. Okay, let's take a look at a compound here, this one. So we saw how carbon dioxide is formed. Carbon dioxide has two double bonds, remember? Let me ask you, let's take a look at carbon monoxide and let's see how it forms. Okay, so let's go ahead and let's draw out the structure, the Lewis-Dot structures for carbon and for oxygen. Okay. All right, let's go ahead and let's see how they can get together. So carbon monoxide is an actual molecule. These two atoms are bonded together. Carbon monoxide is the one of the products of combustion, of incomplete combustion, and we'll talk about that in chapter 11. But let's go ahead then and let's take a look at how carbon monoxide can form. Okay, so let's go ahead. Those are the two pieces. If you can imagine, then let's go ahead and let's these two here. Okay, and these two here, we look, and that seems pretty reasonable to us. A double bond forms between carbon and oxygen. In this case, then oxygen has its 8, okay, but carbon only has 6. So, what happens in this case here when we have then a situation in which, and that's it. I mean, there's no other way that you can go ahead and recombine these together to pair up the electrons, because oxygen at this point has no more unpaired electrons. The other two are still paired, and so it can't bond. There's no way that it can do that. Okay? There's no way that carbon and oxygen carbon then complete its octet by pairing other electrons. Okay? All right, and so what we're going to see then, and this is what we'll talk about hopefully tomorrow towards the end. I think we're running out of time here. That if we measure the bond, let's just say then that we have this bond between carbon and oxygen. Okay? We can measure what's called the bond energy. Okay, so we can measure what's called the bond energy, okay? And these bond energies are different for different bonds. So in terms of bond energies, then a single bond, okay, is going to be less than a double bond, which is going to be less than a triple bond. What am I saying here? The single bond is the weakest of the bonds. The triple bond is the strongest. When we measure bond energies, this is the energy needed to break a bond. Okay? And so it takes less energy to break a single bond than a double bond. It takes less energy to break a double bond than a triple bond. And again, we will talk about this here hopefully tomorrow. Okay? But the reason why I want to point this out to you then is that when we measure the bond energy, the bond between carbon and oxygen. Now understand, there is a bond that exists between carbon and oxygen, or else we won't have the molecule carbon monoxide. So when we measure the bond energy for this molecule right here, we see then that it is equivalent to that of a triple bond. Okay. And that's what we notice. The bond energy there for between carbon and oxygen is equivalent to that of a triple bonded carbon-oxygen atom bond. Okay. So how is it that a triple bond can form? And so we can use that to help us draw the structure here. Because right now, there is no way that we can account for that triple bond. Okay. So what we do then is we say this. Okay. What carbon and oxygen can do, or what we say that they may do, is that the oxygen here, there is a lone, it takes one of its lone pairs here and it shares it with carbon, which means that, I'm sorry, let me go ahead and do this, which means that this third bond of the triple, so it will be a triple bond, folks. It will be a triple bond. Okay. But the third bond of the triple bond, okay, so let's go ahead and draw that in. The third bond of this triple bond here, the carbon does nothing. The carbon does not contribute to it. And so therefore, oxygen takes this, these two electrons here, and it shares it with the carbon, okay? And carbon does nothing. Okay? Okay. And that's what this particular bond here, okay, this particular bond that forms right here, we refer to this bond right here as a coordinate covalent bond. Now, a coordinate covalent bond, and this is where things get a little weird for us, you guys. A coordinate covalent bond doesn't actually exist in nature. This is just a way that we as humans can account for the fact then that carbon monoxide is a very stable molecule. It's a very stable molecule because it has a triple bond. So the reason why carbon monoxide kills us is because it's a very stable molecule. And then when it gets into our bloodstream, it binds much better with our blood, with the hemoglobin in our blood, replacing the oxygen, and thus, we no longer can get oxygen to our body, and thus we die. Okay? And the reason for this is it's not easy to break up that bond because it is a triple bond, and so that bond is stable. It is a triple bond, and so with that said, then we also need to know we also know that both atoms have to have their octet. And the only way we can account for that now is by saying then that oxygen shares one of its lone pair electrons. Okay? And so this coordinate covalent bond is our way to explain how a triple bond, in this case, can form even when carbon doesn't have enough electrons to share. Okay? And so if you notice here, if this coordinate covalent bond forms, if it does form, now both atoms have their 8. Just go ahead and count it. We have them 2, 4, 6, 8 for oxygen here. We have 2, 4, 6, 8 for carbon here. Okay? And so when we go to summarize the molecule here, okay, the carbon oxygen molecule is made up of one triple bond, okay, and it has 2 lone pairs. Okay, because these 2 electrons here, they end up, they're not bonding, they end up pairing up. Okay, and so what you're going to end up seeing is that we have the 2 lone pairs, and that is the structure for carbon monoxide. It's formed by this bond here that we refer to as a coordinate covalent bond. So, all right. Yeah, I know. It's not. It's weird. Weird things happen on the at the electronic level, at the electron level. Okay, things really weird things happen. It gets worse, folks, as you go on. When we start talking, when you start learning more about quantum mechanics, it gets weirder. Okay? But when you get to that point, please come back and share with me yours, because you would have gone way beyond what as far as I got. Okay? All right, let's go ahead then and let's do one more quickly. We're running out of time here. Let's do the ammonium ion. Okay, let's do the ammonium ion here. Take about a couple minutes. Now that you know about the coordinate covalent bond, use it to your advantage. So we know about a single bond, double bond, or triple bond. A coordinate covalent bond is not a 4th category of bonds. A coordinate covalent bond is just a way that we can try to connect the dots together so that a molecule that we know does exist can form and still have all of the atoms meeting up with the stability rule, the octet rule, or the duet rule. Okay, so with that said, take ammonium right here. Thanks, we're running out of time. Let's do the same thing here. Finish up with the ammonium ion here. And what we'll do tomorrow then is I will start with ammonium here, and we'll compare answers. We'll compare how you draw your ammonium with how I'll present it to you tomorrow. Okay, so try your best with it. Yeah, those 4 options. Okay, let's see how you connect these 5 atoms together, and then we'll go over it tomorrow. Okay. All right, folks. Have a good rest of your day, and please come by and see me if you have any questions about how we draw these structures, and then well, I'll go over it with you. Okay. All right. Have a good day, folks, and I will see you tomorrow. Okay?